Okay, so we're going to take a look at a last section of this chapter on thermodynamics, which is called the standard enthalpy of formations. When we calculate delta H in the previous section on Hess's law, what we obtain is a delta H value under the specific condition that that reaction is conducted. That might be temperature of 1000 degrees Celsius, it might be a temperature of 100 degrees Celsius, it might be a temperature of 10 degrees Celsius, and the corresponding pressure values that go along with that temperature value. Now, that obviously makes life a little difficult if we have to get delta H value for every specific reaction condition, because there's going to be so many different conditions that it's possible to run a reaction at. And it would be a lot easier if everybody is using just one standard value. And in fact, scientists in this case have developed a set of conditions where everybody is using that when they're referring to enthalpy values. And that condition is called the standard condition. It's a specific set of conditions that's referring to what we call the standard states of a substance. So standard state for a gas is that it has to have a pressure of 1 bar and it has to have ideal behavior. 1 bar and 1 atm are fairly close numbers, so we can think about it as having a pressure of about 1 atm. If you're running a reaction where the gas is at a pressure of 10 atm, then that would not be a standard state condition. So in order for you to get your enthalpy as the standard enthalpy, your pressure value has to be about 1 atm. What about if you are running a reaction for a substance in an aqueous solution? Then the concentration of that substance has to be 1 molar. So if you're running it at 0.01 molar, then that is not standard state. And again, the reason we do this is not because we're saying you can't run a reaction at 0.1 molar. It's just that to make it so that everybody is speaking about the same values, we're using the standard state value. So again, the standard state is just sort of a reference value. What about for a pure substance? If you have pure solids or liquids, elements or compounds of that, solids and liquids, the standard state is just the most stable form of that substance at 1 atmosphere and the temperature of interest, which typically is 298 Kelvin. The reason for this is because things like solids, there's not just one type of solid for a given substance. For example, for ice, there's actually many different types of ice that you can form depending on pressure and temperature combination. The way we know that our delta H is the standard state delta H is when you have a degree symbol next to your delta H. So in fact, you'll see the symbol right here, delta H with a degree next to it, and that refers to standard enthalpy of a reaction. So that means that when you run that reaction, you're running it specifically under these standard state conditions. Now let's talk about a related concept here, which is something called the formation reaction or formation equation. Formation reactions are reactions where you form 1 mole of your compound or a product, doesn't have to be a compound, could be an element as well, from its elements. So what's the example? So let's say you have CH4 here, that's your compound, right? Methane. You're going to form this 1 mole of this, so the coefficient is always 1 here on the product side, from its elements. What are the elements that exist for methane? Well, it's going to be carbon and hydrogen. So carbon, the standard state of carbon, the most stable form of carbon is graphite. So we're going to write carbon, graphite, plus hydrogen. What's the element form of hydrogen? Well, it's going to be H2 gas. So that means that it's going to be carbon, graphite, plus hydrogen in the gas form going to form methane. And we balance it in such a way where we get 1 mole on the product side. The delta H that we get from this type of measurement is what we call the standard heat of formation or standard enthalpy of formation. The symbol is delta H subscript F. Okay, F here represents formation enthalpies. Value here is negative 74.9. Now, how do you get this number? Well, people have done many of these formation reactions because again, it's one of those reference values that's going to be easy to use, and later on you're going to see how this is going to be used in calculating enthalpy of reactions. So you can find this in usually some type of thermodynamic tables, and there are many of these type of tables. The one that I've attached for this class, it's called Appendix 4. It's from a textbook that we used to use. So I'll just show it to you right now. And this Appendix 4 looks like this, and you can see here that there's a column for the substance and the state of the substance, and then there is the delta HF value. You can see that there's 2 other columns here with 2 other series of numbers. We're going to skip those right now. That's not going to be important for us in this class. It's going to be important in a future class. But right now, all you need to look at is here, this number on this side. Okay, so you see that for manganese oxide, for example, formation enthalpy at standard state is negative 385 kilojoules per mole. You look at something like nitrogen gas, you see that value of 0. I'm going to go back to that in a second to explain why that's 0. If you look at HNO3 aqueous, for example, it's going to be negative 207. So different substances are going to have different values, right? You can see this one right here, NO, that's 90 kilojoules per mole. So the value of these enthalpy of formation is not always the same. In fact, it's different for different substances, and you just have to look up on this table, Appendix 4 table, in order to find out what exactly the value is. So we can look at NaCl, that's an ionic compound. What would be its enthalpy of formation? Well, if you write the reaction, it's going to be Na, which is a solid state species, and then chlorine is a gas, and it's Cl2. So we have half of Cl2, right, when we balance it out. You might be surprised that there's a fractional coefficient here, but that's okay when you're writing formation reaction. This is the only reaction where when you write fractional coefficients, it's okay to include, because remember that that value that you get from that table is always referring to 1 mole of product. So this number can't change here, it has to be 1. The numbers on the reactant side, the coefficients would have to adjust such that you get 1 on the right side. Now, some of you might be okay with knowing that H2 is the element state for hydrogen, but how many of you know that the graphite form of carbon is the more stable form of carbon? Why not the diamond form of carbon? So this is where you go back to Appendix 4 and you look for the delta HF that gives you a value of 0. So when you look at carbon here, carbon has 2 different solid forms, graphite and diamond. Graphite is 0, diamond is 2. That means that when you make diamond, you actually need to put in enthalpy, but when you make graphite, you don't. So graphite is exactly the element itself, because when you go from the element to the element again, then all you get is an enthalpy change of 0. And so that's really the reason why we have enthalpy value of 0. So if you need to know what is the standard state for a given element, let's say you don't know what the standard state of sodium is it a solid, liquid, or gas? All you need to do is go back to that table and look up sodium and then try to find what state gives an enthalpy formation of 0. Whatever that is, that's going to be the standard state. So in this case, it's clear that it's 0 for solid sodium, so that must be the standard state for sodium. So for here, N2, for example, is the gas form. That's the standard state. And most of these are things that you already know, but sometimes for something like the carbon example earlier, whether it's graphite or diamond, you might not know which one is more stable. And so using this table helps you determine which one is the standard state form of that element. So let's try out writing some formation reaction and then finding the enthalpy of formation from the Appendix 4 table that I discussed just now. So here it says, write a balanced formation equation for each of the following species and include the value of the delta H of formation. I'm just going to try to work on a couple of these. So the first one is AgCl. So to write the formation equation, I'm going to need to put the AgCl on the product side and make sure that the coefficient of AgCl is 1. And then I have to think about on the reactant side, what are the elements that make AgCl? Now there's 2 elements, Ag and Cl, so I have to think about what are the standard states for Ag and Cl. What you need to do is go to that Appendix 4 and look at the section on silver to see which value of silver species gives it a delta HF of 0. Here's an example. I am in the silver section right here, and I see that silver solid has a delta HF of 0, so that tells me that silver solid is the standard state element of silver. So I wrote it right here as one of my reactants. I'm going to have to repeat this for the chlorine. I'm not showing it here, but if you look at the Appendix 4, you'll find that chlorine gas, Cl2 gas, is the standard state for chlorine. So I'm going to write Cl2 gas right here. Now, if I stop there, my coefficient will not balance between the left side and the right side because I'm going to have 2 chlorine on the left side. So to balance it out, I do not change anything on the product side. I keep the product the same, just 1 mole of that product, but I can do whatever I want on the left side to make it balance. In this case, I'm going to have to write the coefficient of a half for chlorine in order to balance it out, because half of Cl2 will just mean 1 Cl. And then the value of delta HF would be also listed in the table. Again, I would be looking for that value in all of the species in the table. AgCl happens to be listed in the silver section as well, and it's right here, AgCl solid. So if you look at the value of the delta HF, it happens to be negative 127 kilojoules per mole of AgCl, so that's what I'm going to write right here. I'll do one more example here. For calcium carbonate, I'm going to write calcium carbonate on the product side as 1 mole, and then you would think about what elements make up calcium carbonate. Well, there's calcium, there's carbon, and there's oxygen. So then, just the same as you did with the silver chloride, you're going to look up that Appendix 4 and figure out in what state are they in the standard state. So calcium is going to be a solid, carbon is going to be a solid as well, but specifically in the graphite form of the solid, so I'm going to write it as CgR there. Oxygen oxygen is going to be O2 gas. And again, to balance out the oxygen so that I have 3 oxygen on the left and 3 oxygen on the right, I have to give it a coefficient of 3/2 on the reactant side. Okay. Lastly, I'm going to look up the value of enthalpy of formation in Appendix 4 for calcium carbonate, and that's going to be listed in the calcium section. And you'll find that the value that's listed there is negative 1,207 kilojoules. Now, why is the standard enthalpy of formation useful? The reason is because once we have those values from the table that we just talked about, we're going to be able to calculate the delta H of a reaction pretty much for any reaction we want. Okay, it covers a huge number of reactions that values in those tables. We can use Hess's law to come up with an imaginary path that will take us from any reactant to any product using the formation enthalpy values. How do we do this? Well, the general concept is explained here. When you have a reactant going to product, you can always imagine this pathway. Each reactant is broken down or decomposed to its elements, and then each product is a combination of elements. Now, why are these two steps useful for us in conjunction with the formation enthalpy? Well, the reason is because when you take a reactant, you break it into its elements, what you're doing is basically you're reversing this step, right? The formation step. So if you take a reactant like CH4 and then you break it into its elements, what you're doing is basically you're saying I'm reversing the formation reaction. So if you reverse a reaction, your delta H is just going to be the negative of the formation enthalpy. Okay, so that's the first part right there. If you imagine that a reaction occurs through a step where each reactant is decomposed to its elements, then the enthalpy of each of those steps is just going to be the negative of the delta H of formation for whatever substance you have. Okay, what about when the elements form each of the product? Well, now you're basically doing the formation step itself, right? So if you imagine elements combining to form a specific product species, that's just a formation reaction. So all you need to do is just go to that table and find out exactly what the delta HF is for that specific product. So you can see that calculating delta H for a reaction is really just a matter of adding all the delta HF for the products and then subtracting all the delta HF for the reactant. This is a drawing that illustrates the steps that we just talked about. We can imagine that we take the reactants and we break it down into elements. So each reactant that we have, every time we break it down, that corresponds to taking the negative of the delta HF of that specific reactant. If you have 2 of the reactants, then you're going to multiply that value by 2. If you have 10 of the reactants, you're going to multiply by 10, right? But each reactant is going to have its own unique delta HF. When you form products from the elements, it's the same as just taking the delta HF itself. So in the end, the delta H of the reaction is just going to be the sum of this step plus that step. And that's the value that we're looking for. Okay, so here's a quick example just to show you some imaginary reaction here. AB plus CD goes to AD plus CB. So again, we can imagine, again, why do I keep saying this imagine? Because remember, in Hess's law, it really doesn't matter what path it is that you take, right? The whole point here is that for H itself is a state function. So delta H can be calculated with any path that we can come up with. So here, what I'm doing is I'm taking this ABCD and I just imagine that, okay, in order for me to make AD and CB, I'm going to first have to break AB into A and B. And I have to break CD into C and D. But when I write the reaction like this, all I'm doing is reversing a formation reaction. I'm taking a compound, breaking it into its element. So the enthalpy change is going to be the negative of the formation enthalpy of AB. Similarly for CD, it's going to be the negative of the formation enthalpy of CD. Now, I am imagining, how do I make these products? Well, all I need to do is take those elements that I have now and combining them. So I take A and D and make them AD, the compound. That's a formation reaction. So the delta H must be just the delta H of formation of AD. Same way here, I get delta H formation of CB. What about the overall enthalpy of this reaction? Well, since these are my paths, just like in Hess's law, what I need to do is just add all 4 of these together, right? You notice that if you were to add all 4 of these together, you can see that the A's would cancel, B's would cancel, CD's cancel. All you get back is this reaction right here. And so now what you've done is you've found a path to calculate the delta H of a reaction, and all you're doing is adding the enthalpy of formation of the products, which is these 2 right here, and then subtracting the sum of the enthalpy of formation of the reactant. To write it in a formula form would look like this right here. Delta H of any reaction is the sum of the number of moles times the enthalpy formation of the products minus the sum of the number of moles times the enthalpy formation of the reactant. So let's take a look at how to use that enthalpy of formation formula we just talked about to calculate the actual enthalpy of a given reaction. It's asking us to calculate delta H of reaction from delta H of formation values. You can see this question in your notes as well. So to calculate the delta H of reaction, all I need is use that formula that was given earlier in the notes, which just says that the delta H is going to be equal to the sum of the number of moles of the product times the delta H formation of the product minus the sum of the reactant coefficient times delta H formation of each reactant. So I'm applying it to this reaction. I would take 4 moles times the delta H formation of NO gas, because that's my first reactant, and then 6 moles times delta H formation of H2O gas, which is my second reactant. And then I would subtract 4 moles times delta H formation of NH3 gas and 5 moles times delta H formation of O2 gas. And what I need to do here is just find those numbers in Appendix 4. For NO, it's 90 kilojoules. So if you look at the H2O section, you'll see that there is liquid and gas. You need to find the gas value, which is negative 242. For NH3, it's going to be negative 46. And again, here's NH3 gas. So again, I want to highlight the importance there. If you look at the nitrogen section, you'll find NH3. There's 2 NH3 there. NH3 gas is the one that we're looking for, and that happens to be negative 46. You don't want to use the value of AQ as NH3, which is negative 80, because that would have been wrong, right? Because in this reaction, you're looking specifically for NH3 in the gas form, okay? Just keep that in mind. And then lastly, for oxygen gas, because that's the actual element of oxygen in its standard state, its delta H formation is just 0. So calculating everything together, we end up getting negative 908 kilojoules.